Following on from our question in class today, we have this circuit set up of 4 resistors. We found an equivalent resistance by adding these two in parallel. They gave an equivalent of 30 ohms. Then we added these two in series to get an equivalent of 40 ohms. Then we added these two in parallel to give an equivalent of 15.4 ohms. Now let's say that the potential difference between the top and the bottom of the circuit is 12 volts. So this is point A, this is point B. What we're saying is that the potential difference between A and B is equal to 12 volts. If the potential difference is 12 volts, find the current through each of the 4 resistors. So we can do this with a couple of approaches. Let's use this equivalent circuit idea first. So we know that this circuit is equivalent to this circuit. So whatever current that flows through the top part of the wire here is the same as the current that flows here. So let's look at figure 4 and find the current that goes through this equivalent circuit. So we have the wire, we have the equivalent resistance of 15.4 ohms. There's point A, there's point B, so we know that the potential is 12.0 volts. Using Ohm's law that says V equals IR, we can find that the current I is the total potential divided by that resistance. So 12 volts divided by 15.4 ohms to get a current through that wire of 0.78 amps. So that's the current that enters this circuit. So the current that comes down right here is 0.78 amps. We can add this to figure number 2. Now I could draw right here, but I think I'll just redraw the picture a little bit. So now we're going to back up to figure 2, or figure 3. So figure 3 has our top right here, we've got a 40 ohm resistor here, 25 ohm resistor here, point A, point B, and what we know is that the current that comes in right here is 0.78 amps. This is our 25 ohm resistor, and this is our 40 ohm equivalent resistor. So now we can use what we know to find the current through these two guys. So this resistor is hooked up to points A and B. This resistor is hooked up to points A and B. The potential across points A and B is 12 volts. So these two are in parallel. They have to have the same potential. So this one must have a potential difference of 12 volts, and this one must also have a potential difference of 12 volts. Because they're in parallel, they have to have the same potential. So let's find these two currents. So the current in the 25 ohm resistor is going to be the potential divided by the resistance, 12 volts divided by 25 ohms, to get a current of, oh, hang on, I can't find my calculator. Here we go. So there's a calculator, 12 divided by 25, 0.48 amps. So that's the current that goes through this branch right here. We'll add that to the picture, 0.48 amps. Through the 40 ohm equivalent resistor, the current is the potential over the resistance equals 12 volts over 40 ohms. And we'll do 12 divided by 40, and we get 0.30 amps. We can add that to our picture if we wish. So now if we look back at figure 3 here, we know the current through this resistor, the current through this resistor. So far we've got this one done. Now let's back up and see what we know from figure 2. So we'll just reproduce figure 2 right here. So figure 2 is the one before we've calculated this one in equivalent. So the 40 is the equivalent of this guy. We'll redraw this figure right here. We'll add in the things that we know. So what we know is that this is point A, this is point B. The potential from point A to point B is 12 volts. We know that the current going through the 25 ohm resistor, we found it in the previous part, 0.48 amps. So 25 ohms, 12 volts, 0.48 amps. So now, a couple of ways we can do the current here. probably the most straightforward way is that we know two resistors in series have the same current as the equivalent resistor in series. So if this is 0.3 amps, then this has to be 0.3 amps. So this is our 10 ohm, and this is our 30 ohm. So for the 10 ohm resistor, I has to be 0.3 amps because it was a series connection. And for the 30 ohm, the current has to be 0.3 amps because it's a series connection. If you had forgotten about the fact that it was in series and it had to be the same, well, you could use the fact that you knew the current put out between those 2 points. That was 0.78 amps. What you would know is that 0.78 has got to be this current plus this current. If this one is 0.4, then 0.48, then this one has to be 0.38. So why don't we just put that there for a little notice that the current in equals the current out, so that's Kirchhoff's junction rule, Kirchhoff's current rule. So 0.78 amps equals 0.48 amps plus 0.3 amps. Okay, so tick, we know that that's right. So now we're almost answered. We found the current through the 25 ohm, we've got the current through the 10 ohm. We know the current through this guy, but this is an equivalent of these two. So let's back up to figure number 1, and then we'll find out the currents going through those guys. Grab another sheet of paper, we'll reproduce figure number 1. Okay, there's point A, there's point B. Let's get some stuff in there that we know. This is the 25 ohm resistor that has a potential of 12 volts. It has a current of 0.48 amps. The potential between points A and B is 12 volts. The resistance here is 10 ohms. The current here is 0.3 amps. And this is our 45 ohm resistor. And this is our 90 ohm resistor. So now how are we going to figure out what we're going to do? Well, what we know is that resistors in parallel have the same potential. So for this 30 ohm resistor, we can figure out what was the potential across that. So if we come back to figure 2, we have, this is a 30 ohm resistor. It carries a current of 0.3 amps. So the potential across the 30 ohm resistor, let's add that in right here. So the potential is current times resistance. 0.3 amps times 30 ohms. And that gives us 0.3 times 30, gives us 9 volts. So the potential across this parallel equivalent is 9 volts. And if we wanted to calculate this one, we would see that that was 3 volts, 10 ohms times 0.3 amps. So these potentials have to be the same. So these each have to be 9 volts. And that's because resistors in parallel have the same potential. So what they had in their parallel equivalent right here has to be the same potential that they have right here. If you weren't so sure about that guy, you could go straight from this picture. This one must have a potential of 10 ohms times 0.3 amps. This one has to have a potential of 3 volts. From here to here is the potential across all these guys. So the potential here must be the total potential 12. Take away this potential 3 to leave us with 9 here. So that would be another way to work that out. So now that we know the potentials and the resistances, we can find the currents. So for the 45 ohm resistor, V equals IR, so the current is the potential over the resistance. We've got 9 volts over 45 ohms. That gives us a current of 9 divided by 45, 0.2 amps. For the 90 ohm resistor, you might have a guess as to what this one's going to be. The potential over the resistance, 9 volts over 90 ohms. 9 over 90 will give us 0.1 amps. So then together, we have 0.3 amps coming in here. That current splits, comes down this way and this way. For this resistor, it's a little bit bigger. It has less current, 0.1 amps. This one is a little bit smaller. It has more current, 0.2 amps. So now we figured it out. We've got the current through every single resistor. If we wanted to go on a little bit and find the power dissipated in each resistor, we could probably do that as well. But the problem only asked for current, so we've got that bit done. There is another way we could do this, and we could use Kirchhoff's loop rule or Kirchhoff's voltage rule to solve those, and we'll do that one in another video.